Thank you so much, Earth. Thank you so much for the organizers for organizing this amazing event. So I'm going to talk about post-quantum constructive reduction. This is joint work with Nir Bitansky and Zvika Brakelski. And let me first start by thanking them for the slides. I love questions, so you don't need to wait till the end. I much prefer you guys follow, as we go along. So please feel free to ask questions at any point. I don't have an agenda of finishing everything or anything like that. So I really hope that kind of to explain to you the gist of this work in a possibly interactive setting. Okay, so let's start. So we're talking here, this work is about post-quantum cryptography. What we're thinking about are actually classical cryptographic primitives or protocols. So we have a classical protocol or primitive, and let's say we know it's secure in the classical setting. Okay, so we did all this cryptography before quantum came along. And now we ask, now today, unfortunately, quantum adversaries may come along, and we ask, are our schemes still secure? So the security still hold in the presence of a quantum adversary. Now, of course, the answer is not necessarily. For example, one thing we all, first thing we notice is that we must have post-quantum secure assumptions. So as opposed to having, let's say, the assumption be factoring, now we want the assumption to be lattice-based, LWE, some assumption that we believe to be post-quantum secure, okay? But the focus of our work is actually, let's say our schemes are secure under LWE, okay, or under a assumption that we believe is post-quantum secure. The question is, does the proof of security carry into the post-quantum setting? Okay, so can we argue, is the security proof itself, the proof post-quantum? So usually in classical cryptography, our proofs are by reduction. That's kind of how we prove security. So we say, for example, if I have, what is the proof of security? I say, well, if I have an adversary that breaks a primitive P, let's say breaks a pseudorandom generator, okay, so distinguishes, let's say, a pseudorandom string from a random string, then a reduction can use that adversary to break an underlying assumption, say one-way function, okay, if you're thinking of, constructing PRGs from one-way function. That's how we prove security in cryptography. That's kind of what I want you to have in your head. And my question is, do these classical reduction still hold in the post-quantum setting? For example, do we still know that one-way functions imply PRG, or our constructions, are they still secure in the post-quantum setting? Okay? So again, this is the focus of this talk. Let's consider classical reductions. So classical proof of security, but for assumptions that we believe to be post-quantum secure. Can these classical reductions be lifted to the post-quantum setting? Okay, so do they still hold if A, the adversary A, is quantum? That's the question we ask. Okay? Any questions about the setting? Okay, so at first, of course, we're thinking of reductions that treat or think of the adversary A, use it in a black box manner. Now, not all our reductions are of this form, but almost all of them are of this form. So let's focus on these black box reductions. And now we say, do they still work in the post-quantum setting? Now, in some sense, if the reduction thinks of the adversary as a black box, he has no idea how it's implemented, whether it uses, some quantum things or classical. It's just a black box. So it seems like it shouldn't matter. Like the reduction has no idea. What he just has, input-output access to this thing. So, if you don't think about it much, it seems like, sure, it should. Okay, yeah?
Are we supposed to think of the reduction querying the adversary as a quantum machine?
No, okay, very, very good. Okay, great question. So the question was, should we think of the reduction as querying the adversary as a quantum machine? So no, so here's the thing. Think about, this was done classically, okay? The proof was given before we knew about quantum, before we were worried about quantum adversaries. So I guess my question is, let's look at all the classical cryptography before quantum came along. Okay, we have like dozens of, years of cryptographic research. And the question is, do we now need to redo everything so that it's secure in the post-quantum setting? Or can we just say, it's okay, take everything we did, up, it's magically still secure. That's kind of, so everything, the reduction is classical, everything is classical, but now it's interacting perhaps with a quantum adversary. Okay, and the question, does security still hold? That's a great question, thank you. Okay, is the setting that we're talking about clear? Okay, so it seems, as I said, it seems because maybe if the reduction just talks with the adversary as a black box, it should be able to tell the difference if the adversary is classical or not. So maybe, we're lucky. And of course, if you think about it a little bit, you notice actually we're not that lucky, and the situation is much more problematic. And an easy kind of example of that is in the interactive setting. So consider a primitive P that's an interactive primitive. And so the way the adversary kind of interacts with the primitive, it sends a message, it gets back a message, and back a message. It's kind of an interactive thing. In this case, the way the reduction works often is to say, okay, the reduction will interact with the adversary, will kind of pretend to be the primitive, interact with the adversary, and often what it does, it rewinds the adversary to kind of a middle state in the protocol and reruns him forward again. And now, of course, as we know, well, if the adversary has some quantum state in kind of the midst of the protocol, when we run him, of course, the quantum state gets destroyed, or disturbed, I should say. And then when we rewind, and continue forward, the reduction can get completely useless information, and hence will fail to actually break the assumption Q. Okay? So we knew that this is problematic for interactive primitives. And if we have an interactive protocol that we know, say, is sound in the classical setting, it may not be sound in the quantum setting. Okay, and moreover, actually, we even hinged on this fact. So there's a work of Balkowski et al. That actually constructed, their goal was to prove quantumness. So they said, I'm going to prove to you that I'm a quantum machine. And the way they did it is they exactly gave an interactive protocol where a quantum machine can succeed on, and a classical machine cannot succeed on under LWE. So they actually really showed that the reduction can actually use a classical adversary to break the assumption Q, whereas it cannot use a quantum adversary to break this assumption, exactly because the reduction failed to rewind a quantum adversary, whereas it succeeds to rewind a classical one. Okay, so this is not just kind of a problem of our analysis or anything. This is a real problem. In general, reductions do not carry over to the post-quantum setting if the primitive is interactive. Okay? Okay, so the focus of our work then, we said, fine. How about non-interactive assumptions? Let's focus on non-interactive assumptions. So here you should think of it, the assumption is just getting a challenge, he gives an answer. So you can think, for example, PRG, right? He's given either a random string or a pseudo-random string, he needs to guess. Or semantic security of encryption. He gets encryption of 0, encryption of 1, he needs to guess which one it is. Okay, so the question for such primitives, where there's it's just the adversary just sends one message and that's it, do things carry over seamlessly to the post-quantum setting? And it seems like, yeah, well, now he can't rewind, it's just a non-interactive thing. It should, especially, of course, if you think of if the reduction treats the adversary as a black box, which is what we should think about today. Okay, so it seems like the answer is yes, but actually the situation, even in this setting, is subtle. So, and let me explain to you why. Usually, indeed, the adversary is just a one-shot thing, so he gets a question, he answers, and that's it. But still, the way often the reduction works is by running multiple copies of this adversary. So he says, oh, there exists an adversary? Okay, I'll run him once, so I'll give him one challenge, get a response. Then I'll say, okay, from the beginning, a challenge, I'll get a response. Okay, and then let's start again, from the beginning. So in some sense, the reduction often, the way he succeeds in breaking the assumption Q is by using many, many copies of the adversary. Now, in the classical setting, this is of course not a problem. You have one algorithm, you can run him as many times as you want. In the quantum setting, it may be a problem if the adversary has quantum auxiliary input. So now the adversary may have some advice, psi, a quantum state psi, which he may use to solve to break the primitive P. Okay, so now the problem is, okay, the reduction will run A once, with his quantum state, he'll get the result. But once he measured the result, the quantum state is disturbed. And when he runs them again and again, the quantum states will kind of evolve and may be completely useless. And then A will again, and then the reduction may again fail to break the assumption. Okay, so it seems like this may be a problem. Let me mention maybe one question that can come up is, well, that's not really a problem. Why not just, copy the state? So if you have an adversary, A, that breaks psi, give the reduction many, many, many copies of psi. And now he will run like each adversary with a fresh copy of psi. So indeed, actually, that would work. If you manage to clone the psi, the state psi, then you do have post-quantum security. Exactly because the reduction will not be able to distinguish whether he's talking to a classical adversary or a quantum adversary. He'll just get like answers, and all of them will be valid, all of them will be good, and he'll succeed. Okay, so why aren't we satisfied? Well, how do we copy the state psi? Okay, where did it come from? So we don't know. He got the state psi. Where? We don't know. This state psi may come from, let's say, an intermediate state in some protocol. So maybe I have a protocol. The protocol uses a PRG somewhere. And I'm in the middle of the state. I have a PRG. But the state that the adversary has at that point, if you kind of copy it, somehow, it'll break another kind of crypto primitive that happened before in the protocol. So, so that can be a problem. Who knows, maybe it came from a very expensive pre-processing state that the reduction cannot afford to kind of do again. And more generally, the problem is that you can't clone quantum states, as we all know, okay? And so if you can still make this work, you can still say that if you have an adversary that breaks primitive P with a quantum state psi, then the reduction can break primitive Q if he gets access to quantum state psi tensor. So essentially many, many repetitions of this state psi. But that would be what we call a non-constructive reduction. So yeah, we can break Q, but if we get these clonable states, how we get them, I don't know. So what we really want, we want to be able to actually, if we can break P, we can actually break Q. Not to say, if we had these states that who knows where I'm going to get, then we can break Q. I want to say that kind of, in some sense, that's kind of the win-win nature of provable cryptography. So why do we do all these reductions? Why not just kind of assume security and hope for the best? And if things break, then, come up with new schemes. One of the kind of sell points of this kind of provable cryptography in general is this win-win situation. We say either our scheme is secure, in which case we're happy, and if someone, God forbid, breaks it, then we have advancement for algorithms. Okay, we have a new algorithm. We can actually break. We have some explicit algorithmic advantage. So what we really want is to say, if I have an adversary that has state psi and breaks a primitive, the reduction can use this adversary with the same state and break the assumption. any questions about the goal? So this is that's our goal. Our goal is to say that we can take these non-interactive primitives in the classical setting and lift them to be post-quantum in a constructive way. That the reduction that breaks the assumption, even in the post-quantum setting, is constructive. Okay, it only uses the same state. Question?
Yeah.
Great.
So I just wanted to clarify the right way to think about psi. So like is the reason we can't like generically always copy psi because it's not always like some non-uniform advice? Because I would imagine if it's non-uniform advice, then like you could arbitrarily prepare as many states, but maybe psi depends on the input or something.
Okay, great. So good. So the question was, where does psi come from? If it's just some uniform device that you can generate, you can regenerate it from scratch every time. You're right, but sometimes you can't do that because sometimes this psi comes from kind of, okay, option number one, the adversary got a hand of it from someone, but actually regenerating it takes so much time that in that time you can actually break the primitive P anyway. So now you can say, how did he get it then? You know, if it's so hard to come up, how did he get it? Sometimes you can getting one is easy, but getting two breaks everything. And one way to think about it is actually think about, let's say there's some interactive protocol that uses this primitive in one of the rounds. Okay, so you have like a protocol, and then it uses a semantically secure encryption. Now you say, oh, but this semantic secure encryption is under LWE, so things are still secure. However, when you try to rewind to argue that, oh, things still secure, you may need to rewind this adversary. So you'll need to clone his state in this middle of the protocol. And cloning this state in the middle of the protocol can amount to breaking, like you can't. That can be hard. So in general, actually, kind of generating or cloning the state can be hard, and we see it, for example, for those who are familiar with the Killian protocol for succinct proofs, 4-message proofs for NP. Actually, they're proving security. So you can think of it's a 4-message protocol. The last proof, so we have a proof in the classical setting is easy. In the proof in the post-quantum setting was recently, I'm actually going to talk about it, was given by Chiesa et al., a work from 2 years ago, a beautiful work that we're going to actually refer to in this work. But the hard part that you can think, the last 2 rounds can be thought of like a non-interactive primitive. And their entire work is, you can't clone the state. You can't assume that it's secure and you can clone the state because it will break the crypto that was used in the first round, which is some hash function. So actually, they need to work a lot to kind of do the security without cloning the state. So they did it for a specific kind of protocol, and we want to generalize it for general non-interactive primitives. Okay, can we argue security without needing to clone the state? Okay, any questions? Yes?
So when we say A here, like what kind of an algorithm it is, because let's say it's very close to being deterministic, then we know that the state psi will not be disturbed too much, right? And we can use it again and again by some kind of gentle measurement.
Wait, sorry. So A here is an arbitrary adversary. I have no control over it. So the reduction does not know. So when we prove security, we say there exists a reduction that if it has access to any adversary that breaks primitive P, then the reduction should break primitive Q. I agree that if things are kind of, sometimes A can be a nice A that kind of the measurements are so gentle that it won't disturb your state. Then we're in luck. But it may not be that way, and we don't have control over the adversary. So we want to have security for any adversary, not just for nice adversaries that will help us clone their state or help us make sure that their measurements are gentle. Great questions. Great questions. Thank you. Okay, so let me just mention that this idea of constructive reductions was also targeted in the classical crypto. Okay, also in the classical crypto. So in the classical crypto, the adversary, even if it's non-uniform, cloning the adversary is always easy, that we know. But even in the classical crypto, sometimes we considered reduction. The reduction R was non-uniform. So all we said is like, there exists a reduction. We proved there exists a reduction that gets non-uniform advice. We don't know how to compute this non-uniform advice, but there exists non-uniform advice such that. And this kind of was a bit frowned upon. We didn't like that because this non-constructive nature. Okay, so I guess my point is this idea of wanting uniform reduction, or in classical crypto we call it uniform reduction, but actually the way to think about it in this setting is a constructive reduction. We want it also in classical cryptography. The problem is here, if we don't work, we always get something non-constructive. So we know that we can't clone states in general. So we need to actually, work to get something non-constructive. And the question is, can we even get it? So this is what we're gonna, that's kind of the goal. Questions? Okay. Another goal which we get is what we want is durability. So this is again something then the classical crypto you get for free. But what I mean is I want so the reduction breaks an assumption Q, right? Let's say it breaks one-wave function. Ideally, we want to say that you can use the reduction to invert the one-wave function many times, not just once. Okay, so this reduction gets a state psi, and we prove that it can break the assumption. Let's say invert the one-wave function. Now, in general, because it gets a non-uniform advice, maybe he'll invert once, and now he can't invert anymore because the quantum state was kind of destroyed, or at least evolved to a way that it's not useful anymore. So the question is, can we do it in a durable way that we can continually invert the one-wave function? Yes?
So one of the things that I have a question about is this durability aspect. If you look at classical crypto and cryptanalysis, you worry about not just full breaks, but partial breaks. Mm-hmm. So, thanks. And so if you look at Crystal's Kyber, for example, a lattice-based algorithm, a certain part of it is actually completely dependent on one-way functions. So if you can use some quantum algorithm, say, Grover's, to partially break the one-way function, then the security reduction for that, the post-quantum crypto aspect of it is absolutely weakened.
Right.
And so what I worry about is that, do people consider that break, that partial break, could then also then be cause an advantage in some other way?
Okay, great. Yeah, that's a great question. So I guess no, that's a really interesting question. So for me, I'm kind of simplifying the world here, and I'm thinking, I have a security definition of a one-way function. There's no partial or there's a break if there's a BQP algorithm that inverts with non-negligible probability. Otherwise, it's secure. So I'm making my life kind of easy. I agree with you that actual life is not that easy, and one can consider okay, so this is theory. Of course, in practical, what is a break? We talk about actual numbers, 256 bits. What's a break? If I break it in 194 bits, is it a break? So I agree that in practice, when you deal with actual number and concrete kind of things are much more complicated. But here, I'm thinking kind of in polyland. So in the land of theory, which is much cleaner. Okay, so let me tell you the results that we get. So what we show is that you can actually lift, immediately, automatically, or seamlessly lift a large class of classical reductions to the post-quantum setting in a constructive and durable manner. So let me be a little more specific. We say the following. So we're consider only non-interactive primitives P, and we say that if the reduction A is black box, we always have black box reduction, but as I said, almost all our reductions are black box reduction. We also assume that the reduction is non-adaptive. So non-adaptive just means that, so the reduction sends the adversary challenges, right? We said he kind of thinks that he's interacting with many, many adversaries, and each adversary gets a challenge. The assumption is that these challenges may be arbitrarily correlated. However, they do not depend on the answer of the adversary. That's what non-adaptive means, okay? So again, non-adaptive reduction means that the queries that the reduction makes to the adversary do not depend on the adversary. So do not depend on the answers of the adversary. Okay, so we assume if the reduction is black box, it's non-adaptive, and the primitive P is not a general kind of search primitive. So let's say if it's a decision primitive, like PRG, or semantic secure encryption. Is it encryption of 0 or is it encryption of 1? The adversary needs to guess. Like, it's a decision assumption. This can be made more general than decision, but let's think of decision from now. Then we can make, then the reduction, we can make it, we can kind of change it a little bit to make it post-quantum, to make it constructive and durable in the post-quantum setting. So we can use the reduction. The reduction can take just one copy, a single copy of the adversary, that's all, single copy of the adversary, and use it not only to break Q, but to break Q over and over and over again. Okay, so it can break Q once, but you can still use it to break Q again. Okay. Any question about the statement of the result? Yeah. Great question. The question is, yeah, so we do need to break, so our reduction uses many copies of the adversaries. And all these adversaries will have quantum states. So we will continue to use the state psi that evolved. We just are going to make sure that it evolves in a good way. So you'll see, I'll show you kind of actually how we do it. But yes, we're going to continue to use this quantum state. We have to use it. And I'll show you how we use it in a way that's still useful for us. Okay, so let me just mention, we assume that R is non-adaptive. Why we need to assume that R is non-adaptive? I actually don't know. My guess is that the only reason we assume that R is non-adaptive is because we, the authors, are computationally bounded. I don't think this is an inherent assumption. Actually, I would be very happy if one of you removes this assumption. Okay. We also restricted the P, the primitive, to be a decision assumption. Or it just has to have a few good solutions, like polynomially many good solutions at most. Okay, so there's some assumption about, like the adversary can have at most a small number of valid, solutions or answers that we'll be accepting. That assumption is not because we're computationally bounded. Actually, that assumption, to some extent, is inherent. Because we show actually a counterexample where P can be an arbitrary search assumption. Okay, and if I have time at the end of the talk, I'm going to talk a few minutes about it. Yes?
Can you sacrifice durability?
Good. The question is, can I sacrifice durability? No, actually, the durability we got for free. Okay, we actually, in the beginning, we didn't even ask for durability. So everything I say now, the durability we get for free. Even if we didn't want durability, we can't get rid of any of these three restrictions. And as I said, R being black box should not be thought of as a big restriction because that's most of a reduction like that anyway. But the non-adaptive and the decision assumption, or not be able to be general search assumption, that these two are restrictions. The decision we can't get around in general because we have counterexamples, so that's an inherent problem. And the non-adaptive, I believe we can get around. Okay, any other questions? Okay, so in the last, 10 minutes or so, let me just give you a taste of the techniques. Okay, so our reduction, of course, calls the adversary many times, okay, to break the underlying assumption. That's how this is our classical reduction. And we want to try to argue that it works in the post-quantum setting. Now, if we were lucky, and this reduction only used the adversary once to break his underlying assumption, then we're good. It's post-quantum secure because the reduction, he talks to any adversary that succeeds in breaking the primitive, he breaks the assumption. And this is a valid, he doesn't know if A is quantum or not quantum. So if he talks only once with the adversary, then we're good. However, most of them do not talk once with the adversary. They talk many times to the adversary. And that's when kind of our trouble comes. Okay. So what we really need to do is to kind of bridge between this one-shot quantum adversary and our classical adversaries that just, you can just copy them. Okay, so really, the difference between our quantum adversary and the classical adversary is not really quantum classical. Forget about that. What the point is that the classical adversary is just completely stateless. So the reduction works if he has access to an adversary. He doesn't know how he's implemented. It's a black box reduction. But he has access to an adversary that completely works. He has no state. He doesn't remember what he asked. He doesn't remember that this is the second time is invoked, and the first time, some state was measured and therefore collapsed. He just gets access to the same adversary over and over again. In that case, the reduction works. However, what we have is, so we need to bridge this gap between our one-shot guy that we have that, you run him once and state collapses and, he's useless, to like a stateless adversary that it's like computes the same exact function. You give him a question, he computes the exact same function over and over and over again. So we need to kind of bridge this gap. We know that our classical reductions are applicable. They work if the adversary is stateless. So you just the same adversary one again and again and again. But what we have to our disposal, unfortunately, is this one-time guy. That after you run him once and he's like, I was measured, can't work anymore. So the question is, how do we bridge this gap? Okay, so we bridge it in 3 steps actually. The first step, we show how to convert this one-shot adversary to one that's kind of persistent. He continues to solve the problem. Okay, not with the same state. It actually evolves. So you start by running the adversary with state psi. Then you get after running him, you get a new state, phi. It's not the same state, so he'll behave maybe differently, but he still succeeds in breaking the primitive. So the reduction can use him. And then evolve the state to another state, rho. And then so on and so forth. So it evolves, it changes, but it does not lose its steam in breaking the assumption. So we go from one-shot to persistent. He's continually breaking the assumption, but he evolves. So the first question, how do we do that? So this is a beautiful, beautiful idea. I can kind of happily say genius idea. It's not ours. This idea is due to the CMSZ paper on the post-quantum security of the Killian protocol that I mentioned by Chiesa, Mas, Spooner, and Zandri. So they showed a really, really nice technique of like quantum rewinding, where you can kind of, you measure the state, but then you can kind of restore the state to another state that's a good state. And then you run the adversary and you restore the state. So they have this technique of doing it. This technique is restricted to the measurement being few bits, okay? Or what do I say, decisional assumption. So in some sense, so what they showed, actually, I mean, their work is for the specific Killian protocol, but if you read what they actually did, the theorem that you can extract from it is that any non-interactive and publicly verifiable assumption, so any assumption that you just get a challenge, you give an answer, and anybody can know whether this answer is good or not. So this is not quite a decisional assumption because they had public verifiability, but if they have it, that they could convert a one-time solver to a persistent one. And what we show is actually this publicly verifiable is really not needed. They needed it for the Killian protocol. I mean, they got it. The Killian protocol was like for them, that was enough. So that's what they did. But actually, if you just redo their work and, with a little bit of, quantum, sweat, then you can get rid of this public verifiability. Okay, so what we can show is that any interactive protocol, any interactive decision assumptions, or again, any assumption that the adversary, its answers, he doesn't have many, he has only, let's say, polynomially many possible accepting answers, then we can actually convert, we can restore the state of the solver or the adversary, okay? By the way, one interesting thing from our work is that the fact that you can restore states only for decisional assumptions or primitives is inherent. So that kind of, it shows kind of that this technique can be generalized in one setting, and it doesn't need public verifiability, but it cannot be generalized to arbitrary assumptions. Okay, so that's kind of the first idea. Now you can ask, wait, isn't it actually enough? So now the reduction has an adversary. He can continue to talk, the adversary always succeeds, and now we can break the assumption. So isn't that all we need? Okay, again, we started with a one-shot adversary that only succeeded once. And of course, the reduction can't succeed. He needs someone who succeeds many times. Now I told you, okay, I can restore state. So I can continue, I can give him access to adversaries that always succeed. Different quantum state, but who cares? So the first adversary succeeds, the second adversary succeeds, and so on and so forth. Okay, and these states are not, it's just I evolve the state of the adversary. I never need to clone anything. Okay, everything is kind of efficient. So isn't it good enough? So why can't the reduction just work? And the answer is that while all these adversaries are successful in solving the primitive, where they're successful can change. And it can change arbitrarily. And moreover, it can change arbitrarily based on past questions. So what can happen? Maybe if he asks some question and he succeeds, now on that question or in that vicinity of questions, the next adversary, the new quantum state, never succeeds. So the problem is where you succeed can drift. The solvable kind of set can drift. And so now the problem is if the reductions queries are correlated, if they're all just random, then probably all of them succeed and we're probably going to be good. Still, one needs to be careful, but let's say that may be okay. The problem in many reductions, the reduction does not just send random independent queries. Think about, for example, Goldreich-Levin, if those are familiar, like the hardcore predicate. How do we prove the hardcore predicate is random? The reduction sends the adversary very specific, like he asks x and then x plus e, or x plus the one hot vector. So these are very correlated. They're actually very similar queries. And what can happen is that the first adversary, so maybe all the questions are in this red kind of circle, and if the first adversary succeeds in this circle, then likely the other adversary will not succeed in this circle, because these things are correlated. So that's a problem. So really, in order to succeed, we need the reduction to have access to stateless adversaries, to the same adversary over and over again. That's when it succeeds. We can't give him different adversaries that behave like if they succeed in this query, so now they're not going to succeed on similar query. That's a problem, because maybe the reduction actually needs to ask a similar query. Okay, so again, the problem with just using the CMSZ trick alone, or this state restoration trick alone, is that the new state that we restore can be very, very dependent on the previous state psi. And it can be dependent in kind of an anti-correlated way, or it can be dependent in a way that's against the reduction. Okay, so it can be correlated in a way that we don't know how it's correlated. And it can be correlated in a way that the reduction will actually fail on it. So what we really need is to kind of go from this persistent to kind of memoryless. Memoryless means all the adversaries don't remember what happened in the past. So the second adversary, he doesn't even know what the query was to the first adversary. So where he's solvable or not doesn't depend on that. So really what we want is that's kind of our bridge two, is to make our adversary forget the query. And if it forgets the query, then now where it succeeds in solving is independent of what query it was. So we should be in good shape. So the main thing here is the way we do it, and this is, by the way, the restriction to non-adaptive, which, again, as I said, I do not think is inherent. We show how to go from a persistent adversary that may change kind of arbitrarily, adaptively, each time, to one that forgets it may change. So here we have adversary 1, here we have adversary 2, here we have adversary 3. but adversary 2 is independent of the question that adversary 1 got. Okay, so it's like the reduction talking to different adversaries that are completely kind of fixed ahead of time, if you will. Okay, and don't kind of depend on the, oh, you got query 1, so the new adversary 2 is this way. Oh, you got query 2, so adversary 3 is this way. No, so the bridge here is the one that's memoryless. There's fixed adversary 1, adversary 2, adversary 3. Don't depend on the previous ones or the previous queries. Yeah. Wait, can you say it again? I didn't hear.
Does that mean that the Goldreich-Levin kind of argument doesn't work?
No, so good. Actually, the Goldreich-Levin argument, so we can get Goldreich-Levin to work, let me say, but this was done actually for the specific Goldreich-Levin. There is a paper showing quantum, like post-quantum Goldreich-Levin, so this is not our contribution, but we actually can do the Goldreich-Levin because we're not assuming that the reduction, so let me just emphasize, this is a great question, so thank you. We're not assuming that the reduction is non-adaptive, is not correlated. Okay, so the reduction can be correlated. The reduction can send the first question X and the second question X plus, EI. Yes. What we want is that the adversary, where adversary 2 does not change his behavior depending on the query that adversary 1 got. So I want to change my upstairs adversary, where A2 actually, the second adversary or the state phi may depend on the query that the first adversary got, and therefore where it succeeds may depend on where the query of the first adversary. I want to convert it to a memoryless one, where the A's, A1, A2, they don't know what the previous A's got. And then we're kind of almost there. Oh, I should go, I should end, okay. So let me just say the idea here. So the way we go, so remember we had a persistent one, where every adversary their behavior changed depending on the queries of the previous adversaries. The way we get around it is actually very, very simple. The idea is let's dazzle the adversaries with tons of kind of irrelevant queries. Okay, so we'll just give him a bunch of dummy queries so that he gets out. So let's say I'm supposed to send query 1. I'll sample tons of query 1s. Okay, and now he won't know which is the real one I want. There's one that I actually want. I'm going to give him a ton. Much more than the state, the number of qubits he has to store. So I have an adversary. He has some state. He has some size. Okay. Now the reduction it's gonna run in more time than the size of this adversary, and it's gonna dazzle it with a bunch of kind of dummy queries from the exampled IID from the marginal distribution of the real queries. And the idea is that the adversary won't know what the real one is, and hence likely to forget it. Okay, speaking of the forgetfulness in James' talk. Okay, so the observation here is because the adversary is polybounded, his memory is polybounded, and because it's limited, if we dazzle him with enough dummy queries, he'll forget the real one. He'll forget a lot of them, and the real one probably too. That's kind of the idea. I just want to mention this is where we assume non-adaptiveness of the reduction. So we assume here that the reduction, the queries it sends may be correlated, but do not depend on the adversary's answers. Just because if they do, this is not even well defined. Like what's the marginal? The marginal distribution of the queries now depends on how the adversary behaves. Things become messy and we couldn't analyze it in this setting. Okay, so this is the only place where we assume, well, this is one more place where we assume non-adaptivity is where to dazzle you with kind of IID queries. That's nice to assume. This is where we assume that that the reductions queries do not depend on the adversary's answers. Okay, but that's essentially what we do. So to make the ith query, what I do might meet the reduction. Before the reduction just made the ith query to the adversary, that's it. Now the reduction, we're going to change it. It's going to be smarter. He's going to generate many ith queries from the marginal distribution. He's going to send the adversary all of them. So, I'm going to send all of them, and I'm going to put the real one that I wanted, the actual reduction sent, in a random location. And now what we prove is this kind of information theoretic, kind of quantum information theory lemma that says that if the number of dummy queries, T, is big enough, let's say it needs to be bigger than the state divided by delta squared, then we get delta closeness to an execution that doesn't have the real query. So in other words, we look at the adversary, we give him all dummy queries or all dummy, but in a random one we put the real query. And let's look at the state at the end. How much information does he have about the real query? With type of, he has at most delta bits of information. And we can make delta as small as we want by making T bigger. Okay, so the delta is like T needs to be L over delta squared. So we have control over this delta. We can make it as small as we want. Okay, so let me just wrap up. This is how we get for memoryless. So this is how we get memoryless. And then eventually we just need to get stateless. That's very easy. It's just, we just shuffle the queries. So before we got like memoryless adversaries, we just shuffle them randomly to get stateless. So that's essentially how we get. So let me just summarize quickly. We started, the reduction had a one-shot vector. She needed like stateless, she had a one-shot adversary. She needed kind of access to repeated adversary. The way we got it is we first converted the one-shot adversary to many kind of good adversaries, but very, very dependent on one another. And then we kind of dazzled, used kind of the tons of IID dummy queries to make sure that the adversaries actually don't depend on the queries of the previous adversaries. And then we just kind of shuffle them around to get like stateless adversaries. So that's the idea. I just want to quickly mention that this model of stateful adversaries was also considered actually independently of our work, concurrently with our work, in the classical setting as well. This is a work by a CFP. What they called cosmic security. So it was also considered, also interesting in the classical setting, just to think of the adversaries instead of kind of fixed as evolving with time. So they kind of also tried to lift the security to this setting of stateful adversaries, even though they did not mention even the word quantum, nor was it their goal. Okay, I'll skip the counterexample for search, but there's a quantum counterexample for search. Let me just end with food for thought. So what about adaptive reduction? So as I said, the restriction to not allowing arbitrary search assumption, we have a counterexample. So that we know that's a restriction that we need. But what about the adaptive reductions? And in particular, PRG from one-way function, it turns out if you look at the proof of Hill, it's an adaptive reduction. So we still don't know if we have a durable reduction for PRGs from one-way functions. So I'll leave you with that open problem. Okay, thank you very much.
Are there any questions for Yael?
So my question is a bit open-ended. So it's more about getting your opinion on something. Let's consider the quantum cryptographic setting where the reduction itself can be quantum, the adversary, we know it's quantum. What does it mean to be black box in this setting? Can you assume that the adversary is purified? Can you assume that you have inverse access to the adversary, or should you treat it as a CPTP map? So
the question, okay, so how do we think of black box reduction with everything when everything is quantum? Okay, so let me tell you, I'm not a quantum person. Okay, I'm a neighbor to you guys. So that's actually probably many people here should know the answer to this, I'm guessing. But I'll tell you how I would define it, right? So I would say you still have black box access. You can give superposition over kind of queries, and you get back the superposition over the answers, but you don't know how things are implemented. That would be my answer to how black box should be defined in the quantum setting. So things should be purified, I guess. The oracle should behave in a purified manner, but you still have no idea about the access. Yeah.
Okay, thank you.
Hi, thank you for a nice talk. I was wondering, during your construction, you use randomness to shuffle the queries
Yeah.
to make them memoryless.
Yeah.
Did you need some random number generator to establish this randomness? Or, I mean, I was wondering, is the proof hold if the actual Q and P that you're trying to attack using the adversary is actually a pseudo-random number generator?
So, okay, so I'm thinking you're right that my reduction is, I'm assuming like inherently that the reduction is randomized. So I'm not using a random number generator. I'm just saying, look, the reduction is randomized and it's gonna shuffle the adversaries completely randomly. I'm not actually, it doesn't need to use kind of a PRG to do it. It's just a random reduction. So I am adding randomness to the reduction to do it. I want to say all our reductions are kind of randomized anyway, because the reduction, it needs randomness to sample the query for the adversary. So often our reductions, and actually I'm using randomness in many ways. I'm using randomness to shuffle the adversaries. I'm also using randomness to generate IID kind of queries to the adversaries. So all these dummy queries also use kind of randomness. So you're right that I'm kind of adding randomness to my reduction. So my post-quantum constructive reduction uses, I assume it has access to randomness. Now you're right, if it doesn't have access to randomness, one can ask, is that necessary? But I think most reduction anyway, they have access, like they use randomness. So I'm not sure if it's, yeah, but that's a good point. We do assume that the reduction, when we make it post-quantum, we do like really rely on the reduction being randomized.
Thank you very much.
Yeah, thanks for, that's a good question.
Okay, final question.
Thanks. I see that the time to run depends differently on delta square, like how close you want your execution to be. So if you want to have like a negligible, to be negligible closer, that means that you need to run in exponential time.
Good, you're right. If you want to be negligible close, you need to run an exponential time, but you don't need to be negligibly close. It's enough to be, so if the reduction, let's say so the reduction runs the adversary, the original reduction, runs the adversary some number of times, let's say k times. So as long as delta is much smaller than 1 over k, we're okay. So it doesn't, you're right that if you needed delta to be negligible, the reduction would run in super polynomial time, which is a problem because this reduction supposedly breaks the assumption. I want to assume polynomial assumption. But actually, the delta we need to work with is not negligible. So the way we do it, we say the original reduction, let's say, uses the adversary k times. We're going to take delta to be much smaller than k, like 1 over k over like security parameter or something like that. And then each time you remember a delta, but this delta is like, even if you remember delta all along, okay, k times delta, it's going to be still so small that it won't affect, like it will affect the output by like 1 over security parameter. You can play, if you play, well, there's also how much the epsilon that the adversary, if A succeeds its probability bigger than epsilon, you'll need the delta to be smaller than epsilon. So, but everything is like 1 over poly. So at the end of the day, the delta you'll need to use is not negligible. It's 1 over poly that depends on the success of the adversary, which is poly, depends on the number, the original reduction, how many times it runs the adversary, which is poly. So all these are poly, and the delta will need to be kind of smaller than 1 over these polys. But that's good enough.
Okay, thanks.
Yeah, thanks for that's a great question. Thank you.
Okay, it's more than time to go to the break. So let's thank both speakers again for 2 very great talks.
Thank you.